Hey guys, what's up? Today we are going to be going over our first set of notes for the trigonometry unit in Precalculus. I'm Mr. Flanagan, and here we go. First, we're going to start with the angle and what an angle is. As you can read right here, it's the union of two rays. As you can see, this ray right here and this ray right here form an angle. And you can see it forms this angle right here, which we call theta. It looks like a zero with a line through it. You can also call it alpha or beta. These are all Greek terms. Angle in standard position. So most angles you'll see look like this, at least in this class, where the vertex is at the origin, and then of a rectangular coordinate system, and the initial side coincides with the positive x-axis. The idea is that you will see something that looks like this, where you have this side, so you have the right-hand side on the x-axis, just like that. Then you have degree measurement. It's always measured counterclockwise, so if it's a positive degree measurement, it's always going from like this position and moving leftwards. You could also have a negative degree measurement, and then it looks like it's clockwise, the opposite direction. All right, so you guys know what a right angle looks like. It has to have a 90-degree angle, and it's a fourth of the rotation. So what that looks like here is, I'm going to scroll in real quick so you can see all of my work the best. So you have a right angle with 90 degrees and a 1/4 revolution. So we will see this come right here. That is our standard, as you can see, this standard position right here. And we want to make a 90-degree angle, always going counterclockwise for positive. So a 90-degree angle is 1/4 of the revolution all the way around. That is 90 degrees right here. Now a straight angle, a 100-degree angle, is 1/2 the way around. So again, we're going to start with our standard and work our way to a straight line. That is a 180-degree angle, or a straight angle. And then there's these quadrantal angles, and these are really easy to understand. They're just four base angles with 90 degrees, 180 degrees, 270 degrees, and 360 degrees. When you look at this, you'll see the 90-degree angle we've already done. So that looks like this. Please take these notes. We have a 90-degree angle. We have a 180-degree angle, but we've already learned about those. We also have a 270-degree angle, which is 90 more than 180. So again, you're going to start from that standard position and then work your way 3 quadrants to the left. Right here is what we call a 270-degree angle. And the last is the 360-degree angle, which is the full circle. So we start all the way on the right, and we work all the way around. That is a 360-degree angle right there. Those are just some of the basic things you need to know to start really working with trigonometry. Cool. Well, we're going to talk about some reference angles now. So this is the idea that it's always the smallest angle that you can make from the terminal side of an angle of the x-axis. So what that means is that if this was my line right here, it's the closest angle that can form to the x-axis. So what that is right here, that 30 degrees would be the reference angle here. The closest you can get, the closest angle to the x-axis. Next, we have coterminal angles, and there are a couple different kinds. Coterminal angles are the idea of where an angle is in standard position, angles with the initial side on the positive x-axis, and they can have common terminal sides. For example, right here, 30 degrees is a coterminal angle, but also if we go all the way around, that's 390 degrees. That's also a coterminal angle. And also if you go a negative direction, so if I start and go clockwise instead, that would take me to a negative 330 degree angle. Coterminal angles are the idea, just different kinds of angles to get to the exact same point. Positive angles always rotate counterclockwise, while negative angles always rotate clockwise. Degrees are what we most of the time see. We've seen those in the past, but there's also something called radians, and it's another way to measure how far a circle goes. And then we can talk about the circumference of a circle. This is going to be important for you. This is C, circumference, equals 2 pi r. And then always we're going to assume the radius of our circle is 1 for now, unless told otherwise. One trip around the circle is 1 revolution, which is the circumference of 2 pi. So if I have a circle and I do a full lap around, like if I'm a runner and I'm running around this track that's shaped in a circle, I'm going to travel 2 pi around that circle. All right, cool. 1 revolution equals 2 pi radians, and that's also equal to 360 degrees. Also, you have 180 degrees equals pi, 3.14159, so on and so forth, radians. And 1 radian is equal to pi over 180 degrees, which is equal to roughly 57.296. 57.296 degrees. Again, that's not perfect because pi is not rational, but it's pretty close. All right, let's go to the next thing. Convert each angle into degrees to radians, and then also convert each angle from radians into degrees. So you have to figure out, okay, what kind of thing am I given? I'm given a degree here. So I'm saying, all right, what do I have to get to? And right now I have degrees, so I want to go to radians. So we see right here, the way to get from degrees to radians is to do pi over 180 times the degree. So we have pi over 180 degrees times the number of degrees, which we have 240. And I'm going to make this into a fraction, 240 over 1. Next, I can multiply those straight across and divide, or I could try to simplify those a little bit first before doing that. I know 240 and 180 are both divisible by 60, so I would get 4 degrees on the top and 3 degrees on the bottom, because if you divide them both by 60, that's what you would get. And now it's much easier to multiply. 4 times pi can just be left as 4 pi, and 3 times 1 can just be left at 3. So if you convert 240 degrees into radians, you would get 4 pi over 3 radians. And you can say radians, or RAD, at the bottom. Now you have negative 135 degrees, and you want to convert that into radians. Same idea is you just take pi over 180 degrees times negative 135 degrees over 1. Same process. Go ahead and try that on your own before I show it on the video. It shouldn't be too hard. We can see these are also divisible, this 135 and this 180. They're both divisible, and you can get, 1 second, here and here. This stays negative. It's going to be negative 3 over 4. And you reduce those, and you'll get negative 3 pi over 4 radians. Now, if you were to just multiply straight across and then divide, you should get the same answer. Okay, now we have 5 radians. We're given radians now, and we're trying to get to degrees. So we're going to use this one right here. So we start with 180 degrees. We have that over pi. And we're going to multiply that by the number of radians, or 5 over 1. That will give us 180 times 5 over pi, which unfortunately doesn't reduce at all. But if we put that in our calculator, we're going to get roughly the answer of 286.48 degrees, roughly. You 180 times 5 and then divide that by pi on your calculator, you'll get roughly 286.48 degrees. Next, you have 11 pi over 6 radians. Again, this is the exact same things we did before. We have 180 over pi times 11 pi over 6 because we're using this right here because we're trying to get to degrees. Now, remember, we were going to try to reduce if we can, which we actually can do here. 180 and 6 both divide by 6, and we can actually take a pi from the top and a pi from the bottom. So this will reduce our problem a little bit and make it a little easier. So these both divide by 6, that becomes 1, this becomes 30, and these pi's can cancel out, leaving you with just 30 times 11 over 1, which ends up being 330 degrees. And last but not least, we have negative 4 pi over 3 radians. And our goal here is, again, to get to degrees. So we're going to do it again. Just try it on your own. You have 180 over pi times negative 4 pi over 3. Again, these can reduce, and that's what we'll do. We'll reduce this pi, and we'll just this 3 and this 180. Again, they're divided by 3, so this is 60, and this is 1, and pi's go away. So you would be left with 60 times negative 4, which would give you negative 240 over 1, or just negative 240 degrees. So right now we've learned how to convert degrees into radians and radians into degrees. This is a skill you'll need to know for the future. All right. This part's pretty easy. We're going to sketch the angle with a given measure of like 135 degrees and determine the quadrant where the angle's terminal side is. One thing you want to think about is the quadrants. So if I drew a quadrant up here, quadrants are labeled as 1, 2, 3, and 4. So it starts on the top right and then it goes counterclockwise to label the quadrants. So we have to figure out, all right, where are they at? Okay, so we also know not only are those quadrants, but we know this is 0 or 360 degrees. This is 90 degrees. This is 180, and this is 270. So we can use these things to help us out a little bit. So if we look at 135, we know that's somewhere between 90 and 180. We don't know for sure exactly where to graph it. We're not masterminds or computers, so it's somewhere between 90 and 180. So that's the angle that you're given. And we know we want to find where the terminal angle would be. Terminal angle, again, is what angle would be closest to the x-axis here. And we can see right here would be the terminal angle. And we could say just 180 because the whole thing is 180, and then subtract 35 or subtract 135, and you would get a 45 degree angle. This would be like a 45 degree angle right here. And we know that's in quadrant 2 from up here. You know the next one? This is negative 120. Normally, negative 120, regular 120 would be like somewhere like right here. But because it's negative 120, you don't go starting from counterclockwise, you're going to go clockwise. So you're going to go in this direction. Right here. That is negative 120, even though 120 would look the opposite of that almost. So we look at for our coterminal angle. The idea behind that, again, is where the closest way to an x-axis is, and it's there. So it's 120 minus 180, and that's 60 degrees right there. It's that 60 degree angle. This is in quadrant 3. 5 pi over 6. Oh, this is different. So before we talked about these degree measurements, but now we have these radians. It's honestly the exact same way to do things. It's just you have to think about your uh, coordinate points a little bit differently. This is like 0 or 2 pi. This one is pi over 2. This one is just pi. And this one right here, I'm going to draw an arrow, is 3 pi over 2. So you can use this information to kind of figure out where these things would be. And the first one is 5 pi over 6. One thing I know is it's above pi over 2, but it's below pi. It's not a full pi yet because 5 is lower than 6, but it's over 1/2 of pi. So again, it's somewhere in this zone. Not exactly sure where though. So you have this angle that I'm creating, that's 5 pi over 6. And my goal is to figure out where that terminal angle is, and that's this angle right here. We know this is pi, so we can say, what's pi minus 5 pi over 6? That is 1 pi over 6. That's the terminal angle. That is the terminal angle. Next, we have negative pi over 3. It's a negative, so we know we're going to go in the opposite direction from our positive. We're going to go in the clockwise position. So we know this is pi over 3, negative pi over 3, and that's not a full pi over 2. So it's not even going to go to the y-axis. I don't know exactly where it's at, but I know it's somewhere in this location. So that is negative pi over 3. And you know that is in quadrant 4. This one was in quadrant 2. Sorry about that. And then your terminal angle is actually the exact same here, because the closest way to get to the x-axis is just pi over 3. Cool. All right. Here comes probably the hardest part of the day. For each of the following, name the reference angle, the positive coterminal angle, and the negative coterminal angle. So let's go with the first one real quick. This is 300 degrees. Again, we're going to start in our standard position. That's our standard position. And we know we want to go 300 degrees. That's actually above 270. So it's somewhere in this location right here. That is a 300-degree angle. Our first thing we want to find is the reference angle, which I'm going to label as RA. Again, it's the angle that is closest to the x-axis. So we look here. The closest way to get there is just to add 60. So the reference angle is 60 degrees. Then we have the positive coterminal angle, which I'm going to label plus CA. That is the positive coterminal angle. And this one ends up being from this position right here. We're going to go all the way around. And then again, we're going to go until we hit this line right here. I know that's weird, so I'm going to do it one more time. So we start from the standard point. We go until we hit the line. And then we go one more time all the way around. So that's the normal degree that we had, the 360 or 300 degrees plus 360. So the normal plus 360 a full time around. And when you do that, 300 plus 360 is 660 degrees. That is a positive coterminal angle. The negative one is actually a little easier for this. If we look at a negative coterminal angle, we can go just from this position right here, from the standard position, and then just work our way until we hit the line. And that's pretty easy. It's just negative 60. It's the negative 60. Let's try the next one. So this is negative 110, so we know it goes in this direction and then ends up somewhere in this location. Because it's above 90, but below 180. The next thing we're going to do is look at our reference angle. So that's how far it goes from here to here. And we know that's 180 minus 110, which ends up being 70. The reference angle is 70. Then we have the positive coterminal angle. This is from this position until we hit here. So that's just 180 plus 70, which ends up being 250 degrees. That's 180, is the halfway around, plus the 70 we already know about, which ends up being 250 degrees. Last, we have the negative coterminal angle. I'm going to erase this for now so you guys can see it a little bit better. Negative, so we have to go in this direction, the counterclockwise here, and we have to go all the way around until we hit it again. And to do that, it would be a negative 360, so the full time, and the negative 110, which ends up being negative 460 degrees. Remember, positive and negative coterminal angles cannot be the exact same thing as our original angle. All right, next thing is negative 215. So we have our standard angle, and we know it's actually going to go all the way around. It's negative, and it's not necessarily 270 yet, so it's going to stay right here. That's our normal standard form of the negative 15 degree. Now we want to say to ourselves, okay, we want to find our reference angle. Our reference angle is this angle right here, the closest to the x-axis. So it's 180 minus 215, or 215 minus 180, which ends up being 35 degrees. Next, we have our positive coterminal angle. This one's pretty easy. This one starts from the standard and then works its way to the line, which ends up being the 35 minus the 180, which ends up being 145 degrees. Again, it's the 180 minus, I think I put a 0 here, my bad. It's the 180 minus 35, because you want to see, well, I know the whole way around, or the half the way around is 180, and then you can subtract the reference angle. Next, we have our negative coterminal angle. This one is going to go from the negative position and work its way around all the way until it hits the line again. So that's the original negative 215, then minus 360, which ends up being negative 575 degrees. Again, to go over, reference angle is the angle closest to the x-axis. Positive coterminal angle is going counterclockwise and hitting the line. If it's the first time it hits the line, if it's a positive degree, it just is that angle. If it's not, you have to go one time around again. And then same thing with the negative coterminal angle, where you have to go from the standard position and then work your way clockwise this time. And either it's the first time you hit it or the second time you hit it, depending if it's the angle or not. Okay, we're going to do the exact same thing, except now we're going to use radians, which isn't that bad. Again, we know that it's in the form of 0 radians or 2 pi radians. This one is pi over 2. this one is just pi, and this one is 3 pi over 2. We know that right here is our standard. And 4 pi over 3, think to yourself, is that above pi, below pi? Is it above or below 3 pi over 2? Well, we can tell that it's above pi, because 4 is above 3, but it's not quite 3 pi over 2. It's going to be somewhere in the middle right here. So we know this is normal angle. Our reference angle is this angle right here. And we want to get to pi. All right, well, how do you get to pi? You can get to pi by saying, all right, I know I need 4 pi over 3. Then I would subtract pi from that, because that's what you're getting. That's what you're trying to get to. And then you're left with pi over 3. That is the reference angle, pi over 3. Next, you're going to have your positive coterminal. This one, again, starts from the positive side right here, and then works its way all the way around. Well, we already have that degree, so we got to go one more time around. That's the positive coterminal angle, and that one is the reference angle plus, no, the reference angle. It's the 2 pi plus, so it's one way around. The whole time is one way. 2 pi is one whole time around, and then plus 4 pi over 3. When you add those together, you'll get 10 pi over 3. And the negative coterminal angle is the opposite of that, where you start from here and then work your way till we hit it. And the way you can do that is saying, okay, well, I know that that whole way around is a whole pi. And then we have 2 pi right here. So we have, we have 2 pi the whole way around, but we're not going the whole way around. We're just trying to get to this point. So we can say, what is a full pi minus the reference angle that we already have? So that's pi over 3. And that's going to give us 2 pi, or negative 2 pi over 3. Next, we have negative 7 pi over 4. We know that is above pi. When we go all the way around, it's actually above 3 pi over 2 as well. So it starts here and then works its way all the way around until around this position, because we know that is above 3 pi over 2. If you take them, the absolute values of them at least. So what you gotta do now is say, okay, I know that's 3 pi over 2 all the way around. I want my reference angle. The reference angle is this angle right here. And so we have to say to ourselves, okay, that's 90 degrees or pi over 2. And we want to figure out what this position is right here too, which we know to be sorry, 1 second, pi over 4. Because if you do negative 7 pi over 4 minus 3 pi over 2, that can change to negative 7 pi over 4 and 6 pi over 4. Let's make these positive actually. And then that ends up being negative pi over 4. So you know this angle right here is pi over 4. You have the coterminal angle, the positive. That one's pretty easy. because the idea of it is just going from this position right here and working your way up this way. And when you do that, you just have to do pi over 4, which we already know. So that is pi over 4 as well. The negative coterminal angle is not as easy. This one is when you go a full time around and then hit that line again. So that's negative 2 pi and then minus the negative 7 pi over 4, which ends up being negative 15 pi over 4. And then the last one, we have, I'll cross this out, we have negative 17 pi over 6. If you change that up, that can look like 2 full times around, over 2 full times around, because if you think about it, you could change this to 2 and negative 5 pi over 6. I guess I would put the negative out front. So you know it goes 2 full times around. It's like 1, 2, and then a 5 pi. So like over here. So that's what that angle looks like. I know it's kind of gross. So what we got to do is figure out the reference angle at this point. Right here is the reference angle. And you know that's the 180 minus 5 pi, which ends up just being pi over 6. So you have reference angle, find that again by doing pi minus 5 pi over 6, which is the angle, and you get 1 pi over 6 for the reference angle. Then you have the positive coterminal angle. This is when you are going to start from here and just go until you hit this position right here, which ends up being a full pi because it's the 180 degrees, and then the other pi over 6. So it'll be pi plus 1 pi over 6, and that ends up being 7 pi over 6. And then the last one, this is actually a little easier because we don't have to go all the way around. We just go until it hits right here because that's not the actual angle. So the negative coterminal angle ends up being negative 5 pi over 6. Cool. This part ends up being a little easier, I think, than the last part. This is arc length. The idea is for the circle with a radius r, an essential angle of theta radians. Theta is just the idea of a variable. Subtends or intercepts an arc whose length s is given by s equals radius times theta, where theta is in radians. It has to be in radians. If it's not, you have to convert it. So we're going to find the length of the arc of a circle of radius 4 meters subtended by a central angle of 1/2 radian. So again, our goal is to just find the length of the arc, which is this s right here. So we just say, all right, s is equal to r theta. Think about the things that we know. Well, we know the radius is 4 meters. So we have length equals 4 meters times the theta, which is 1/2, because the central angle is 1/2. So just 4 times 1/2, or 2. So we know s is equal to 2 meters. We know that because the meters unit is given to us right there. The next one, same idea, find the length of the arc of a circle with a radius of 10 centimeters subtended by a central angle of 120 degrees. So we have this S equals r theta, and we know r is equal to the radius, while theta is equal to your degrees, but it has to be in radians. And unfortunately, right now, it's in our degrees. So what we have to do is we have to convert it, and the way you can convert it is by doing 120 degrees over pi and multiply that by, sorry, not by pi, over by 1 times pi over 180 degrees. These can both reduce. They're divisible, and you can get, by 6, you can get 2 over 3. That means 120 degrees is also 2 pi over 3 radians. So you know that's the theta that we need. And we know the radius is 10 centimeters. So we can say S is equal to 10 times 2 pi over 3, which ends up getting 10 times 2 is 20. So you have S equals 20 pi over 3 centimeters. You can also always put this on a calculator as well, 20 times pi divided by 3, and get a decimal answer. But that's 20 pi over 3 is an exact answer. Again, we're talking about arc length. Arc length is this idea, where you just have the length from, let's say, point A to point B. That's the idea of arc length. That's what we just did. But now we're going to do something a little bit more advanced, which is the sector area. So while this might be the arc length, a sector area is the shaded in green area right there. So let's look. This can be found by using the formula area equals 1/2 times radius squared times theta. Theta, again, has to be in radians, and you have to convert it if you don't know it. So you know the central angle is measured at 3 pi over 8 radians. Great, we already have it in radians. We have the radius as well. So our goal is to find the area. Area equals 1/2 r squared theta. So that means we have A, the area, equals 1/2 times the radius, which ends up being 4. So we have 4 squared times theta. Theta in this case was 3 pi over 8. When we do order operations, we do 4 squared. So we have 1/2 times 16 times 3 pi over 8. That means you have 8 times 3 pi over 8, or just 3 pi. Because 1/2 times 16 is 8, and you have 8 times 3 pi over 8. 8 and 8 will just cross out, leaving you with just 3 pi. So that's the area of the sector, but we also want to find the arc length of the sector. And again, we can just use the formula that we already know, which is S equals r theta. We know the radius already. The radius ended up being 4, and theta was 3 pi over 8. We can just multiply that and get 3 pi over 2. So you have 3 pi and 3 pi over 2. Remember, these are in centimeters, so you will want to say centimeters. Centimeters squared for this one, and just centimeters for this one. And the last one is find the area of a sector of a circle with a radius of 3.5 feet formed by a central angle of 65 degrees. Again, same thing, but at first we have to convert our degrees into radians, and the way you do that is doing pi over 180 and multiply that by the degree, which is 65 over 1. These can reduce, and you will get eventually 13 pi over 36. Okay, that's the angle you're going to use. And we have the radius of 3.5 feet. So we can say area equals 1/2 times the radius, which ends up being 3.5. So 3.5 squared times theta, which was 13 pi over 36. When you do that, you're going to get roughly 6.95 feet squared when you put that in your calculator. And then if you want to find the other one where you do S equals R theta to find the arc length, what you can do is say S equals the radius, which ends up being 3.5, times the theta, which is 13 pi over 36, which we've already converted, and that ends up being roughly 3.97 feet. That's it. So quick review. We went over what degrees meant, what the normal degrees were. We went over how to convert from radians to degrees and degrees to radians. Figured out how to find the terminal side, what quadrant it would lie in. We learned how to find the reference angle, positive coterminal angle, and the negative coterminal angle. We learned how to find arc length as well as sector area. Good luck, do your best, and I will see you for the next video.